Okay, so for today's lecture, I will go to chapter 12, 12.6, and maybe complete the 12.6 for now, and maybe last 40 minutes we will continue to have some exercise. So I hope you don't mind if we continue the chapter 12 because of the schedule. Okay, so 12.6, and then after that we will have exercise for your midterm. Okay, we will start in a couple minutes. So if you want to scan the QR code, you can scan the QR code now. Okay, we will start the course. I will share the screen. Okay, last time on chapter 12, we finished the 12.5. Let me reveal a bit. So 12.5, we are covering distance. So distance between some point to other plane, we can measure using this formula here, which is the all the ax, by, c, z, and plus d is all the plane equation from the plane equation, and a plus b plus c is also from the plane equation, the normal factor from the plane equations. So by doing that, we can measure the distance, and this is some example that we have done previously. So after 12.5, what we are going to do next is, it's called the quadratic surface. Let me make a new page. Okay, so one more time. Today I will continue 12.6, and then at the later half, or maybe 30-40 minutes before the class ends, I try to have some exercise for chapter 10 and 11. But before that, let me finish the 12.6. So 12.6, it's called the Quadratic Surfaces. It's actually cylinders and quadratic surface. Okay. So what is the definitions? So first, the definitions for the cylinder. It's not just the geometric definitions that we want, but cylinders as a surface. Okay. So it's a surface that consists of all lines that are parallel to a given line, and pass through to the given curve, to the given plane curve. And the surface, we can sketch the surface. Sketch with it's called tracing. It's actually just a term. If we are trying to sketch, I will tell you how to sketch and what is the basis that we are going to need. Okay. So maybe from these definitions, it's the important thing is it's parallel. Okay, but how do it look like? Okay, so first let me give you example. Let's try to sketch z equal x squared. Okay. Now from this z and x, as of course this is the 3 dimensions. Okay, see 3D space. And from this definition or from this equation, we are not seeing any y, right? So we are missing y-axis or y informations. So if we want to make 3D space, and again, from this 2D projection, from 2D, it's a parabola, right? Parabola, probably something like this. So this is z and x, right? So if we are trying to replicate the parabola into the 3 dimensions, let me make a 3D spaces. So x, y, and z. And maybe make it longer here and longer there. Okay, so this is our parabola that we are expected in z and x axis, right? So we draw first maybe in this origin. Okay, maybe that is our parabola. Okay, now like we have done before in I think 12.1 and 12.2, introduction of 3 dimension. So if we are missing y, then in our curve or in our real space, the y will be in infinitely positive and infinitely negative. So in all axes of y, we will have all this parabola. So we will have parabola here, all around the y. So all with y, and it will create a surface. So that's a surface. Okay. So if we want, we can draw like line like that. And then draw another line like that. Okay. And this becomes our curve or our surface now. So this is z equal x squared. Okay. And it's actually continuously to the infinite negative and positive infinity here. So it's going to infinite points. Okay. And the parallel line that are in our definition are this line. So all line here, all is parallel each other, right? And it will following the parabola z is equal x squared. Okay. Now from this picture, we can conclude that that is our definitions of cylinders. So this is called cylinders. So cylinders means not only just like this tubular shape, but also any surface that has a parallel line, okay, for all like each all line, and they are passing through to the given plane curve. Okay. Now another point or another example that I need to show you is exactly this tube. Okay. So another example. And maybe two example. Okay. So we have x squared plus y squared equal 1. And the other one is y squared plus z squared equal 1. Okay. Now, we now have x, y, but missing z. And here we have missing x, right? And similar to the previous cylinders like this one, we are missing y here, which means in our z here, we will have an infinite point. Okay, so the height will be in terms of z level will be infinity. Okay, so we can draw. Okay, of course, if you are just seeing the equations, these equations means a circle, right? In terms of xy plane. So if this is xy, this is x, this is y, and this is z. Okay, so we will have a circle in xy plane, and the circle has a radius equal 1. Maybe we start from this origin like this one. Okay, like that. And maybe I will having another circle here, another circle here. Okay, that's our cylinder, and it's a tube. It's a tubular. Okay. Now the parallel line is this line all around the surface. They are parallel each other. Okay, and you can see that that is parallel. Okay, so again, this is having infinite amount to the positive z and negative z. Okay, another tubular is y and z. It's similar but different axis. Now we are looking at the YZ plane, the circle. And in terms of x, it will be having infinite amount for positive and negative. So if we want, we can make a circle. Like that. And maybe another circle here. And maybe here. Okay. Yeah, I hope it's looks like a tube. So this having infinite point like that. And also this is the parallel line that are in our definition of cylinder. So this is our cylinder of y squared plus z squared equal 1. Okay, now we have two cylinders. Okay, so in terms of three-dimension space, if you are seeing this like a circle equation like this, x squared plus y squared, it's not a circle, but it's actually a cylinder, okay, in 3D space. A circle is if you are seeing from a two-dimension, maybe from the top or from the bottom, you will see this circle. But in reality, in 3D space, we are seeing the cylinders. Okay, so that's the first part of 12.6, the cylinders. The next part, I hope you can follow the concept, follow the idea for the 12.6. Most likely, 12.6 is about curve, sketching the curve, and the curve behavior and properties. Okay. The next section of 12.6 is called Quadratic Surfaces. So by definition, this is a graph of a second-degree equation in three variables: x, y, and z. And general equation are, let me write, it's quite long, so let me just write first. This is just a general equations, not necessarily the quadratic surface that we want to learn, but this is just a general one. Okay, that's the general equations for the quadratic surface. So the quadratic surface means, okay, it has mostly second-degree equations, which means you will get this terms of squared, okay, x squared, y squared, and z squared. Okay, and other terms are combinations and just a linear one, and also a constant there. Okay, but most likely you will have two equations. So if let me write a, b, c, and j until j are all constants, and by translation and rotation, which means if we rotate the equation or the curve and we translate them, we move them, we can make into two bases of equations. So first is this equations. And secondly, okay, and if you look at the squares here, we will learn that the quadratic surface is a counterpart of a conic section in 3D. Let me write some conic sections formula. So conic sections, if you remember, you have this, right? It's ellipse. And you have maybe this hyperbola. And also you have the parabola one. Or maybe x squared is also fine. This is also, you can switch x and y. And it's depend on a is greater to b or b greater to a. The ellipse will be different. Okay, just quick review for a conic section, because we skipped that in chapter 10. But I believe you guys have a good concept for conic section, I hope. So let's just continue to quadratic surface and what are the examples that we will going to learn and draw. So for the first one, let me give you all the examples, and then we can have conclusion at the end of the chapter. So example, let me write the equations first. Okay, that's the first one. So the question is to sketch this curve, or sketch this quadratic surface. Okay, if you have any idea how to sketch, you can try to sketch this. But let me explain a little bit. Okay, so here you have x squared, okay, y squared divided by 9, z squared divided by 4 equal 1. Okay. First thing, because it is 3 variables, you are not really going to see directly from the equations, right? Okay, unless you know the quadratic surface beforehand. But because you already learned that we are at least know this, right? Which means we can define or we can distinguish ellipse, hyperbola, parabola. Okay. So how to distinguish that form into our questions here? The first is, imagine that one of this variable, for example, is x, it's removed, or you are making a constant. And you have 2 variables, y and z. And in yz plane, you have an ellipse, right? In yz plane, you have an ellipse. Same thing. If you will learn that if you replace this with a constant, then you will have x, z plane, and you have an ellipse, the same ellipse, right? And same thing, if you replace z with a constant, you will have also an ellipse, right? So let me write some terms here. So if, okay, let me write if z is 0, then it becomes an ellipse, okay? And we can also write z is equal constants. We also still have an ellipse. It's still an ellipse. But in every level on K here, we will have an elliptical trace. Okay. And same thing if we are going to let x equal some constant, we will have this. And same thing if we have y as a constant. Okay. And we will know the maximum of each ellipse from their length, the major length, right? So probably this all equations seems difficult or confusing. Let me just draw and see what it's look like. Okay, first we have these equations. So first is this equation, x squared plus y squared equal 9. So we will have, let's say we are equaling z with 0. So when z is 0, x is having length equal 1, maybe here. And y is 3, because it's 9, right? So this. So this -3, and this is 3. So in x and y, xy plane, we have this ellipse. And now the other one is YZ. This YZ. So Y is 3 and Z is 2 because it's 4. So Z is maybe here and the other one is here. So it starts from here, going there, and going there, and going here. Okay, I hope you can see that the ellipse, okay, in YZ plane. Okay, now the other one is XZ. X is 1 and Z is 2. So it's going to look like this. Okay. Okay. Now, maybe it's my drawing is not really smooth. It should be like if you know the American football, the rugby, it's precisely like that. We call this form is ellipsoid. Okay. Now, what this terms means, this K means that they have, this is their maximum and this is also their maximum. So they will have a trace. For example, we want to trace this XY plane in Z level. So we will have going up here, going up here, going up here, and maybe going down here, going down here, going down here. And we want to also measure the tracing from the red color here. So here, 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 and this also their tracing. Actually it's a lot like that. But I want to just to show you the tracings, okay? And also the tracing from here. And also to behind that, okay? I hope you guys can see that. But maybe in the last session, I will show you the real tracing and curve, maybe using the graphing calculator. Okay. But this is the ellipsoid. Okay, because all the traces are ellipse. Okay, that's the first one. This is the first one. We have at least six surface. Okay. Any questions? If you guys want to ask or maybe want to review the previous part, just type in the chat box. Okay, which part you want to look at. Okay, now the next part is another example. So another example, the equations will be z equal 4x squared plus y squared. Okay, the same as previous example, we can make one or one variable become a constant or become just a zero. if you look here, z equal 4x squared. This is our parabola. Z equal y squared, also parabola, right? But when 4x squared plus y squared equals some constant k, or maybe 1 if you're familiar with ellipse, then it's ellipse, right? So we will get 2 parabola and 1 ellipse in the one quadratic surface. So on this is on xz plane. This is on yz plane. This is on xy plane. So if we want to make the drawing, the sketch, okay, I think the z negative it's not necessary. So start from z equal y squared. Z equal y squared is just a normal parabola, like that. Maybe it's too small. Okay. Yeah, maybe like that. And on xz plane, another parabola. Okay. And let the this equal 1. Okay, so and I think I need to make it closer to here. So it should be going here. Okay, now it's looking better. Yeah. It should be like that. Okay. It's like a face. I mean for the flower, like that. But with a parabola curve on its body. So we call this elliptic paraboloid. Oh yeah, by the way, the ellipsoid, it can be a sphere. Okay, it can be a sphere. As long as they have the this is ellipse. So if they are a circle equations, 3 of this plane, then it will be a sphere. Okay, but in general we call it just ellipsoid. Also here, we can also make this ellipse become a circle. If you have the equations become circle, then like for example, if this is z equal x squared, plus y squared. Then it will be a circle, not an ellipse. Okay. And from here we can make the shape like this, or maybe from like this, or maybe to other side like that. Depends on equations. Okay. Okay. If you want to trace the parabola, for example, from all this surface here, from the green one, you can have this tracing to up until here, and also behind that, and also the blue one from here going to the front and going to the behind them. Okay, but as you can see, we can draw just fine elliptic paraboloid. The other example, I think this one is a little bit complicated in drawing, but let's try to draw first. So sketch the z equal y squared minus x squared. So if you are seeing the equation now, you will see that we will have, if we are equaling z with some constant k, we will have an hyperbola. If we are having the, so this is c equal k. So if we are having x equal k, we will have c equal y squared minus k squared, which means this is a parabola. If we have y equal k, we also have parabola, but different parabola from the previous one. So this is k squared minus x squared, also parabola. This is open up, this is open to the bottom. Okay, now let me draw this tree curve, and then let's combine all these three. It's going to be a little bit difficult, but let's try. So first is z y squared minus k squared. Okay. Okay. Now z equal y squared is here. Okay. Now imagine k in a -1 and 1. Because it's squared, it will be a positive 1, right? So it will be the same y squared minus 1, right? So here and here, the space is, or the curve are translated below, and also here also translated below. Okay, so you will have, so this is the true origin. So you will have the tracing is like that. So you will see a line that is connecting here, which is, this is the the extreme point of the curve, of the parabolic curve. Okay, that's the first illustrations. The second illustrations is z k squared minus x squared, which is this downside, or open to the opposite sides of the first curve. So let's draw that. And maybe I will use the other blue. At the very origin here, uh, at this point, or maybe I will make another extension. Okay. So this will be the parabola there. Okay. And then we can also imagine the um, the x maybe the k. Okay. Okay, maybe -1 and 1. Same thing. It's going to be squared, and it will be a positive. So 1 minus x squared. So 1 minus x squared is going to be maybe from here going up a little bit, from here going up a little bit, and this will be the curve. Okay, I hope you can see what I'm trying to make here. So this positions is changing. Okay, so look, this change in positions. Okay, I hope you can see that. Okay, so the curve are changing based on. Okay, so you will see like that. Okay, they are changing in the extreme point. Okay, now the last one is the hyperbola. Hyperbola, y squared minus x squared equal k. This one is a little bit complex here. Okay. Now the k value, it can be negative or positive, right? And depends on negative and positive, you will get the parabola, the hyperbola. It can be in terms of like that, or like this. So we'll have two hyperbola. So let me make the first one. So at the -1, it will be maybe down here. Maybe this is 1 and -1 to make it easy to see. Maybe that is the hyperbola. And the other one is maybe around here. Okay, maybe around here, like that. Okay, you see, if you are seeing from the sides, it's here. first one and the second one here. And this is Z. And this is X. Okay. Get it? Okay. And the other one, the other parabola is here. Let me throw that. And maybe here. Okay. So it's going to be up here. Different should be different. Should be here. Okay. Or if you want, in terms of C and Y, this is going to be here and here. And the below parabola, a hyperbola here. Okay. Okay, I hope you understand. I'm projecting to Z XZ plane and YZ plane for the hyperbola. Okay. So basically, why we have two hyperbola is because of this negative. Okay. So let me write down here. So if you have first is positive, we have that one. And if we have the negative, we have this. This, and it become the opposite. Okay. And when you have y squared minus x squared, because y is positive, then your hyperbola is this. Okay. And because your x is positive, then this. Okay. So the hyperbola will crossing the x-axis. That's the difference. Okay. Okay. Tong, you want to ask the parabola on YZ plane? Which part? The previous example or this one? Okay. Okay, here. Okay, so let me just clarify something so that you are able to see what my point is. So we have two parabola, right? So first is z equal y squared minus a constant, and z equal negative x squared and plus a constant. Okay, the constant having squared, right? And this constant can be positive, can be negative, right? So because constant can be negative, can be positive, I'm just taking a random number that's easy to count, that is -1 and 1. And if we are compute that, we will have, because it's squared, we will have both same results 1, right? So we'll have y squared minus 1. So this, the middle is just k equals 0. This part and this part is -1 and 1, but they both are resulting the same. So they are translated down 1 unit. Okay. And this part is plus k squared, right? Or if you want to write, maybe write like that, also fine. Okay. So the k we can just assume and maybe use the simple number -1 and 1. Both are resulting the same +1, right? So we will have from here we will have z is 1 minus x squared. Okay, so 1 minus x squared is this parabola and this parabola. Okay, and this is just a -x squared. So it will going up to here from origin and going up here. Different from the previous one where it's going down here and going down here. Okay, okay. Is that clear enough for the parabola? Okay. Okay, now we already draw all these three conic sections, the hyperbola and two parabola. And the question is how to combine all together. Now that is actually really tough questions. So first, we combine these two. If you see this parabola, let me combine here, here, and later there. Okay, and then combine the hyperbola from here, and maybe from below here. Sorry, and here. Okay, let me make the final drawing. If you want to check, you can check later the real curve. Okay. Okay, let me use the green color. So the first one, let's make the parabola here. And then make a hyperbola here. So make hyperbola here. It's actually long, but I will cut here just to limit the picture. And then the other parabola is this. So that, and then maybe here, and then that. And then the below part is another hyperbola. I think too close. Should be. Okay, it's quite. Let me check. Yeah. So this is the parabola. This is also the parabola. Oh, this is the hyperbola below, and this is hyperbola at the top. Let me make more clear here. And also here, oh wait, wrong color. Okay. Yeah, and you can trace the parabola here along the line there. And you can trace the parabola here and up till going down there and going down there. Yeah. It's quite complicated, but later if I show you the real picture, it's kind of easy to see what it's look like. If you know the so I'm drawing a, it's actually a horse, but it's look like a goat. But uh, but this is the important thing that I want to show you. It has the saddle, right? This picture is actually looks like a saddle, and we call this this point in the middle here. It's called saddle point, and the whole thing is called the hyperbolic paraboloid. Okay, we still have three more left for the picture, but I think I will skip that for now and go to your chapter 10 and 11 exercise. I think I will focus more on chapter 11. So let me just go there. But before that, any question from here? Yeah, this is, I think it's quite complicated. So if you are trying to see from here the tracing of hyperbola like that, and tracing from here, tracing from there. But if you are in a uh, graphing calculator and you can sketch the 3D curve, it will look nicely done. Okay. Okay, now we are going to try some exercise. Let me go. Yeah, we have done here. Yeah, let me move to another sections for the exercise. Okay. Maybe the first is wait. Okay. Let me make it bigger. Let an and bn, they are both positive, and let the series of AN is convergent, which of the following are always true? It can be more than one answer, so it can be multiple answer. So option A, uh, if the series being converged, then okay, that's the questions. So it can be more than one answer. You can try to check all the options there. And I think in terms of this type of questions, there are several things that you might want to start first. Like for example, the option B is easy um, to be determined, right? It's easy, and D should be also easy, but it's having several calculations. A is also from definitions. You can try to make some conclusions. I think C and D are you need some assumptions and calculation. Okay, anyone get some idea to solve this? So if you check the option B, if you check the answer, if you are using the absolute value there, of course this will be an, and it should is positive. And this makes also this convergent, right? So this will be converged, obviously converge absolutely. And for A, so if you have maybe, for example, letting this series equal some constant, okay? And this will be its inequality. It's having a constant value for the series. So this is because the option A say that if Bn is converged, okay, so then we can assume that it has some constant value there. And because A also converge, and when you multiply with A and here, it will be like that. And because AN is converge, this AN converge, so it will be also then this will be the same as, and because AN is converged, then the whole thing become converge. Okay, get the logic there? So A is okay, B is okay, so that's true. Now let's look at C. Now the option C say that the limit of this an over bn is 0. Which means this is the limit comparison test. But is it all true for all conditions? Now it's quite tricky. You need to find an and bn that are in terms of when you are using the limit comparison test, it can be 0. So the one options that you might have is this. This form is usually easy to be determined with the limit comparison test. So n plus 1 and n plus 1 squared. And both an and bn are positive. Now, if we are looking at this an, and let's make a new integer k. If you are start from 1, then I will make it into k squared. Actually, it's the same like this one, but I'm changing k. It is n plus 1. Okay. So from here, we can set up the limit comparison test. Which is going to be 1 over n plus 1. And this will be 0, right? This is our limit and infinity, okay? But from here alone, because we cannot make a conclusion because we need to make sure what is AN and what is BN. So AN is a converge, but BN is just 1 over k. It's diverge. So we have conflict here, which is we are not true. The C is not true. Okay. Number D, the option is D. Because in the questions, it say that the AN is convergent. Okay, so that's the first thing. The AN is convergent, which means because AN convergent, then limit of AN should be 0. This is by divergence test. Okay, remember. But remember, if limit AN 0, AN is not always convergent. But if the series already convergent, the limit should be 0. Okay. Now you have 1 plus AN from the option D. So 1 plus AN, of course, is greater than 1 plus 0, right? So ln 1 plus AN is greater than ln 1, right? And by using limit comparison test, so we are comparing 1 plus AN and AN. Now we are going to use some L'Hopital rule here. And if you want, you can exchange the AN with some T. Okay. Let's say T going to be positive 0, and T is 1 over N. But if you're just using the AN, it will be the same results, I think. So from here, using the L'Hopital rule, and you derive both top equation and bottom equations, it will be 1, which is converges. So option D is also in our answers. So all except C. So A, B, D are true. Okay. That's the first example. Okay, next example. Let me move one page from here. Don't worry about the notes. I will attach the recording. So the next questions is maybe I'm giving you two questions. So first is if ln 1 minus x is equal, and this is like that. So this box is that's the first one. The second one is find sum of the series. This is the series. Okay, let's do questions first. The second question is, I think it's quite, you need several minutes, I think. I think the first one is shorter. So you try that two questions. Okay, I will maybe solve the first one. So let me move to here. Okay, so if you see the ln 1 minus x, first, if you find this kind of questions, like you have a functions and then you need to make a sum in terms of sum, what you can do is you can think derivative or integrations. So in this case, let me integrate, let me derive first. And this will be negative 1 over 1 minus x. Okay. And if you remember, the 1 over 1 minus x is our x with power of n, right? But it has a negative, so it is negative. Okay. So it's oh, sorry, I forgot to make the sum. Okay. Now here, let's make the 1 a negative 1, 1 minus x, and then equal. Let's make not n. Let's make k to differentiate with the other one, to distinguish from the other one. This x, and then this is minus there. Maybe it's minus here. Now what we are going to do, we want to make to this ln form. We need to integrate and integrate. Okay. Okay. Now we can just integrate like usual. This become ln 1 minus x, become our original equations, equal. We have negative, and then this is k, and we just integral the x with the power of k divided by k plus 1 and plus c. Okay. And we can write down these terms in n equal 1. So we are shifting the power. So it's become n, and it's become n, and it's negative. You can check this c. C will be 0 if x is 0, because ln 1 is 0. Okay. So the answer will be negative. This is the answer. Okay. Now, how to find the sum of the series? Okay. The second question. We have to describe what is sum of the series. If you remember, sum of the series is you have a functions, and you can make it into a sum. Or you can use telescoping sum. Telescoping sum means you need to make the form of the functions, like for example, this is the sum, and you need to make it in this form, and it's having the n and this another n, maybe n squared or maybe just n. It's not important, but at least telescoping sum means from for some particular n until infinity, you will have, for example, from a minus b and then plus b minus c, and you are going to do that until you have the last part in which you have maybe 1 something minus maybe n, the last part. Okay. So you can simplify this, become this. and this become canceling. And this canceling mean this is the telescoping sum. So like you have a whole expansions, and you kind of like zooming in using a telescope and become just 1 over a minus 1 over n. Okay, so similarly, what we are going to do is just that. So from here, the first thing we need to do is we need to arrange the equations. Let me write the question one more time. So first, we arrange this become okay, and then we arrange the squared. It's become this. We factorize the n squared minus 1. And then by using the logarithmic property, let me just write the ln n minus 1 plus ln n plus 1, okay, minus ln n squared. Now this n can go here. This 2 can go to the front. So you will have ln n minus 1 plus ln n plus 1 minus 2 ln n. Now, this is quite a tricky. You need to think and try some form and arrangement. Okay, so you have ln n minus 1, ln n plus 1, and 2 ln n. And now, to make this ln becomes a telescoping sum, which is you have something minus something. So we need to arrange, because we have minus here and we have 2 here. Let's make into 2 parts of ln n. So you have ln n and then minus ln n. Okay. Now we already have this negative here. So let's make this negative as in telescoping sum, okay, like this one. So I will combine this part with this and this with this. Okay, so let me just write the order first. So first is this, okay, and second is this. Or if you want, we make in the bracket, and this become minus, and this become like that. And now this is becoming n minus 1 over n minus ln n over n plus 1. And giving the sum at the front, now we can set up some n and try to make it into our equations. So ln, it's half, and then minus ln 2 over 3. That's the first one. And plus, let's try 3. So ln 2 over 3 minus ln 3 over 4. Now you see we have make telescoping sum. We'll stop here, and let's say we will have the last part is is this. So all the way here is canceling up until here. So our conclusions, we will have this part is 1. So you can answer it's ln half or negative ln 2. Okay. Get it? Okay, I hope you get the idea for the telescoping sum. This is quite hard actually. Thinking from this part to make into this arrangement, it is quite hard, and you need to at least having several minutes to try and error, trial and error. Yeah. So that's the 2 questions. So I think we don't have much time left. So I hope you get the idea for the exercise today. And the 12.6 at the very beginning, we mentioned that. So next time is the midterm on Tuesday, and Thursday we will have the continue for quadratic surface, and also maybe we will move to new chapters. Okay. I hope we can have a fixed schedule next week, and we will meet on class on Tuesday for the midterm. So see you on midterm. If you have no questions, we'll end the sessions now. So you can leave the meeting if you want. But if you want to type in questions, yeah, you can type in if you want. If no, then we will stop the courses until here. Okay, any questions? Okay, if no, then I will stop the recording.